All right, so today we're going to be talking about a concept called mole ratios, but first I want to just dial it back and we're going to use an analogy to start. So I'm going to teach you how to make a s'more. I was a camp counselor for many, many years, and one of my favorite things about the summer is the smell of a campfire and making s'mores and singing songs together. So in my version of a s'more, and yours might go a little different, we're gonna have 3 chocolate squares. So 3 of these little chocolate squares, 1 marshmallow, and 2 graham crackers. So that, and then 1 more graham cracker. And that is what goes together to make a s'more. So if we were going to create some elements for it, it would be 3 chocolates, 1 mallow, and 2 graham crackers make a s'more. So this right here would be the recipe for a s'more. And I just wrote it kind of like how we would write it in chemistry class with elements. So here's my question. How many s'mores can you make if you have 9 pieces of chocolate? Well, if I have 9 pieces of chocolate and I've got unlimited amounts of everything else, each s'more needs 3 chocolates. So I could make 3 sets of s'mores that each have 3 chocolates to make use up my total of 9 pieces. Okay. If I wanted to do that mathematically, it could look like this. My 9 chocolates to start with, and the ratio of chocolate is 3 to s'mores is 1. So each one s'more needs 3 chocolates. Okay, so 9 over 3 would give us 3 s'mores could be made. Okay. What if we had 3 marshmallows? How many s'mores could we make? Well, assuming we had as many chocolates as we needed and as many graham crackers as we needed, I could make from 3 marshmallows that all need 1 mallow per s'more, I could make 3 s'mores. Okay, and again, if I did that sort of mathematically, I would start out, well, I have 3 marshmallows, and I know the relationship between marshmallows and s'mores is 1 marshmallow to 1 s'more. So that means I can make 3 s'mores. We're going to do the same sort of thing, but this time we're going to do it with elements, compounds, and real chemical reactions. So we say that 1 mole of C5H12 right here reacts with 8 moles of O2 to form 5 moles of CO2 and 6 moles of H2O. So the numbers out in front are called coefficients. And they tell us how many units, and in the units are moles, there are of something. And so we basically are writing a chemical reaction is kind of like a chemical recipe, okay? And this is our relationship. There's 1 pentane and 8 oxygens come together. They rearrange to form 5 carbon dioxides and 6 water molecules. So stoichiometry is basically the calculation of how do I figure out either how much of one reactant I need in my reaction, or if I have a certain amount of reactions, how many products can I actually form. So we're going to use the coefficients, which are the numbers out in front, and our balanced equation, and some dimensional analysis. And we're going to do that all together in some examples. What's important is the mole ratios. And the mole ratios are made up from the coefficients of our balanced equation. Okay, so that is like the relationship between one substance to another substance in a specific balanced equation. So if you look at this balanced equation, I can write a bunch of different mole ratios, I know that the relationship between pentane and oxygen is 1 mole of pentane to 8 moles of oxygen. And it doesn't matter which one I write in the numerator. I could write that same relationship with the fraction flipped. 8 moles of oxygen is equal to 1 mole of pentane. Okay? And you can do that for any of these relationships. For example, between carbon dioxide and water. I know that there's 5 moles of carbon dioxide for every 6 moles of water. There's 5 moles of carbon dioxide to every 8 moles of oxygen. And so basically, you can show the relationships between any of these reactants and products with your balanced equation because you're just relating the relationship between the coefficients, the mole ratios. So let's do some examples together. So for example 1, it says how many moles of water are produced when 4 moles of oxygen are reacted. So what we have is we start out with our given information, 4 moles of oxygen. And what we're looking to do is to go from moles of oxygen to moles of water. And so what's going to be important is the mole relationship between water, which is 6 moles, and oxygen, which is 8 moles. So for every 8 moles of oxygen, we're going to produce 6 moles of water. So this fraction right here is going to be where our mole ratio ends up getting used as a conversion factor. So we can put that right in there. Our 6 moles of water is equal to our 8 moles of oxygen. How did I know where to put them? Well, my moles of oxygen are in the numerator of the top of this fraction, and so they're going to go in the denominator of the next fraction. Okay. From here, we're going to just do our math out. You're multiplying the numbers across the top, so 4 times 6, and then dividing by any numbers on the bottom, divided by 8. So our answer will be 3 moles of H2O. Again, that came from multiplying your 4 and your 6 together and then dividing by the denominator 8. So 24 divided by 8 ends up with 3 moles of oxygen are produced. Let's try our second example. How many moles of pentane are needed to produce 10 moles of CO2? So we're looking at the relationship between the pentane and the CO2. So we've got 1 mole of pentane and CO2 to every 5 moles of CO2. Okay, so I start out with 10 moles of CO2, and I'm going to need to take my moles of CO2, and that's going to go in the denominator of our next fraction. Okay, so moles of CO2 cancels out moles of CO2, and we're going to put our moles of pentane on top. Again, noticing that our mole relationship here is the coefficients of our balanced equation. Okay, to do this math out, I multiply the numbers in the top of the fraction and then divide by any numbers in the bottom of the fraction. So 10 times 1 is 10, divided by 5 would be 2 moles of pentane. Let's try one more problem. This problem is unique because it's asking us how many grams of water will be produced from 1 mole of pentane. Okay, and this is different because we're going to have to do 2 different steps. Our first step is going to be our mole ratio, and that's going to convert our moles of pentane to moles of water. Our second step is we're going to use our molar mass of water, and that is going to be able to convert from moles of water to grams of water. Okay, remember your molar mass is how many grams are in 1 mole of a substance. So we'll have to add up our molar mass. Okay, so let's do our first step, and that's going to be looking at our mole relationships. So we have 1 mole of pentane to 6 moles of water. So we'll put our 1 mole of pentane on the denominator and then our 6 moles of water in top. The second thing that we're going to do is we're going to add our molar mass of the water. So what you notice here is I have 18.02 grams of water equals 1 mole of water. Let's remember where that came from. So H2O means there's 2 H's and 1 O. So we're going to use the molar mass from the periodic table of each element. So there's 2 H's, so 2 times 1.01 gives you 2.02 grams per mole. There's also 1 oxygen, which has a molar mass of 16.00. So we're going to add that to the 2.02 grams to get 18.02 grams. So that's where that came from. If you need some help, just come see us for some help. Okay? And then to solve this out, we're going to multiply all the numbers across the top. And in this case, just divide by 1. So any number divided by 1 is just itself. So we get 108.12 grams of H2O.